is going to tell us about composite Fermi liquids in the lowest Landau level.
Yeah, so thanks to Nigel and Chris Green for inviting me to present some of our work here, and it's been wonderful. As Jayendra said, I'm already learning a tremendous amount. I should also thank many of the other speakers today for having introduced many of the things that many of the topics that I'm going to talk about. So the work that I'm going to talk about, my long-standing collaboration with Chong Wong, who's in the audience. It's a bunch of papers in the last 1 year, and very closely related is this beautiful work by Son that Bert Halperin already mentioned, and related work by Max Metlitsky and Ashwin Vishwanath, and a number of other papers which I will not have time to discuss. So let me very, very quickly go over the introduction, since what I'm going to talk about is exactly the same situation, the same physical problem that Bert Halperin talked about. We are interested in 2D electrons in the quantum Hall regime, and we are interested in this, what Bert famously called the unquantized quantum Hall effect at nu equals a half. And experimentally, what we have is a metal, unlike the quantum Hall fractions, but where rho xx and rho xy are both non-zero, but rho xx is much smaller than rho xy. Okay? And the theoretical problem is that an incompressible fractional quantum Hall state is something that you get when you fill certain rational fractions of a Landau level. Here we again have a rational fraction of a Landau level, nu equals a half. And the large degeneracy of the Landau level is in the fractional quantum Hall state is split by the electron-electron interactions to give you a gap state. Here, for this compressible metallic states, we have to understand how interactions manage to split this degeneracy to produce a metal. Okay, so that's the theoretical question. And the standard theory, of course, is which Bert reviewed, is this composite Fermi liquid theory of HL and R. So I don't really have to say anything about this, since you just heard Bert describe the story. So the essential idea is to take Jane's composite fermions and apply this idea of a composite fermion to what happens at nu equals half when these fermions see zero effective field, and that leads to the formulation of an effective field theory in terms of these composite fermions that's coupled to an internal gauge field with a Chern-Simons term. And this theory, again, as Bert and Jayendra reviewed, actually has been enormously successful. Led to many explanations of many phenomena experiments and to predictions of new things. I won't go over this again, since I think by now it's been discussed sufficiently often. So I want to jump directly to some of the unsatisfactory aspects, which again Bert reviewed. So this issue, so Bert described it, but let me re-emphasize this issue once again, that you expect that any theory in the quantum Hall regime should make sense if you project to the lowest Landau level. So the projection of the lowest Landau level means that if your interaction is much smaller than the Landau level spacing, it should be legitimate to forget about all the higher Landau levels and define the problem entirely in the lowest Landau level. Okay? Now, in the HLR theory, there is a mean field effective mass. If you take the HLR procedure and do mean field, there's an effective mass, which, as Bert described, is just the bare electron mass. And the question is, what happens if you send the cyclotron frequency to infinity while keeping the electron interaction strength fixed, which formally corresponds to taking to the limit of bare mass of the electron going to zero, right? So in the limit that the bare mass goes to zero, something needs to happen and produce for you a finite effective mass for the composite fermions, for the theory to be sensibly defined in the lowest Landau level. And this issue, there was a lot of discussion of it in the late 90s, but the dust never really settled. And there's a famous, well-known problem with the standard formulation of HLR. So the other issue, which also Bert described in his talk, is that if you do restrict to the lowest Landau level, then the theory has an extra symmetry at nu equals a half. And this symmetry is not manifest in the HLR description, just as Bert emphasized. HLR is blind to this symmetry, and that's the particle hole symmetry. And this again was identified in the 90s in this work of Kivelson et al. But there was no real resolution in the 90s. So the particle hole symmetry, to borrow this joke from Shankar, it's a question of whether you regard the lowest Landau level at nu equals half as half full or half empty. Right? So you can either start from an empty Landau level and fill half the states and reach the half filled Landau level, or start from the filled Landau level and remove half the electrons to reach the half filled Landau level. And particle hole symmetry is the statement that these 2 points of view on the half filled Landau level are equivalent. Okay. It's useful for what I'm going to say to think about this symmetry a bit more precisely. So I'll very quickly, there's essentially one aspect that I want to highlight, which is that formally, the way in which we would implement the symmetry of particle hole is to expand the electron operator on the basis of operators that create or destroy electrons in Landau orbitals in the lowest Landau level. And because these orbitals are the Landau level wave functions are complex, the action of particle hole conjugation requires you to complex conjugate these Landau level wave functions, and therefore particle hole symmetry is implemented in the lowest Landau level as an anti-unitary symmetry, much like time reversal is implemented as an anti-unitary symmetry in quantum mechanics. Okay, so the symmetry of a half-filled Landau level, lowest Landau level, with say a two-body interaction is there's a charge conservation U1 symmetry, and then there's this anti-unitary particle hole symmetry. Okay, now numerical work, when truncated the half-filled Landau level, truncated the lowest Landau level, and using a two-body interaction where you expect the symmetry to be there, shows that there's a metallic ground state at nu equals half, which in fact preserves the symmetry. Right? Old work by Rizai and Haldane, but modern work just in the last 1 year through DMRG as well. Now, since the HLR theory is not in the lowest Landau level, it's hard to directly address this issue of whether the ground state is exactly particle hole symmetric, right? Within the framework of HLR, right? So, you could try to do the kinds of things that Bert talked about, which is to calculate some physical quantity and see whether the predictions from HLR match what you would expect if you had exact particle hole symmetry. But, if there's also a numerical statement that the ground state is exactly particle hole symmetric, and that, is hard to address within HLR, though it may be possible, but it's not been addressed, right? So there's some other related theoretical problems. Here, I use the word problem not as an issue. Just say these are that people over the years have thought about. So if you think about electrons at other even denominator filling fractions, for instance, a quarter, there's no particle hole symmetry, and there's of course no particle hole symmetry. And empirically, it's known that you still form a metallic state, right? Presumably a composite Fermi liquid. But the issue of the nature of a lowest Landau level theory remains, even without the issue of what happens to particle hole. Because particle hole is no longer an issue, but the issue of what happens when the bare M goes to zero still remains, right? And it's also useful, conceptually in thinking about these kinds of questions to think about them not just in the context of electrons, but also think about bosons and in the quantum Hall regime, and think about composite Fermi liquids of bosons as well. And at fillings, at odd denominator fillings for bosons, so 1 over 2p plus 1, the HLR procedure again leads to a compressible metallic state. And once again, we can ask about the fate of such a state in the lowest Landau level, obtained by taking the bare mass of the boson to zero. And again, just like for electrons of these fillings, for bosons, microscopically, there is no particle hole symmetry either. There's no notion of filling a Landau level for bosons. But nevertheless, this projection to the lowest Landau level and the fate of the theories are issues that need to be addressed. So I want to describe some progress in thinking about these problems, some of them old and which I'll mention briefly, but some new. Now, there was some very important work way back in the 90s on this problem of composite Fermi liquid of bosons at nu equals 1. There's a derivation of a purely lowest Landau level theory of a metallic composite Fermi liquid state in this paper by Nick Reed. I'll briefly describe some of the results of this very old work, because it turns out that the results are in fact conceptually in many ways very similar to the results that to this picture that is developed just in the last 1 year for a particle hole symmetric theory of the electronic composite Fermi liquid at nu equals half. So one of the things I would like to do at this time is to bring out some of the similarities between the new picture that we have for electrons at nu equals half and this older theory for bosons at nu equals 1. Okay? So this particle hole symmetry for the electronic composite Fermi liquid at nu equals half was really kick-started by this beautiful suggestion by Dan Sohn that the composite fermion perhaps should be thought of as a Dirac particle. Okay? So by now we have a field theoretic way to understand why this suggestion may be correct, and I'll briefly talk about that, and we can give a simple physical picture of the particle hole symmetric composite fermion. And there's very extensive numerical calculations through the DMRG technique that seem to verify many aspects of this proposal that the composite fermion is a Dirac particle. Okay? So let me describe some of these developments now. So what I'm going to do is to start with electrons at nu equals half and start with the physical picture of this particle hole symmetric composite fermion to build some intuition, and then talk about the field theoretic derivation of this Dirac composite fermion first. And then, if there's time, I would like to make this comparison with the existing theory of existing lowest Landau level theory of bosons at nu equals 1, developed by Reed, and show the similarities and some differences as well. And finally, talk about composite Fermi liquids in the lowest Landau level at generic filling fractions, and develop a theory that's inspired by these two theories that works at any filling fraction in the lowest Landau level limit, of course, typically without particle hole symmetry. Okay? So let me start with the physical picture. So here I'm going to wave my hands a little bit. The idea is to build some intuition of these composite fermions at nu equals half. Okay. So I want to start with an old physical picture that existed in the 1990s for what composite fermion looks like in the lowest Landau level. So it's a wave function for the lowest Landau level, which, for some reason in the literature, everyone calls it the Rezai-Reed wave function, though it's really part of the same family of Jain wave functions that, for the gap states that Janendra described in his talk. So it involves taking electrons, writing the wave function as J minus Dj squared, which plays the role of converting electrons to composite fermions, and then putting them into a Fermi C, that's the Slater determinant, and then projecting to the lowest Landau level. Now, the main, in this wave function, as opposed to the exact singular gauge transformation done in the field theoretic description, what one does is to bind vortices to particles as opposed to binding flux to particles. So the process of binding vortices to particles, formally at the level of the wave function, it means you do Zi minus Zj squared rather than Zi minus Zj squared divided by modulus of Zi minus Zj squared. When you bind a vortex to the particle, the amplitude of the wave function is suppressed in the vortex core, right? So there's some depletion of the electronic density in the vicinity in the vortex core. So consequently, one should really think of a vortex as a correlation hole that's attached to the electron. And so the net electric charge of the composite fermion will be reduced from that of the electron by an amount that's equal to the charge of this correlation hole. And at nu equals half, you can make a reasonable argument that the electron is bound to a 4 pi vortex, which has charge depletion of minus E, so that the composite fermions in the lowest Landau level are exactly electrically neutral. Okay? So that's the first statement, that the composite fermions are neutral. The second statement is that even though they're neutral, they actually carry a dipole moment. And the idea here is that you're attaching some vortices to the electron, but these vortices don't actually sit exactly on top of the electron. They are displaced away from the electron by a small amount or rather by an amount that depends on the center of mass momentum of the composite fermion, and the direction of the displacement is perpendicular to the momentum. Okay, so this is a simple classical way to understand this statement. If you think about two oppositely charged particles moving in a magnetic field, the direction of their drift velocity is perpendicular to their separation. Okay, so that's the essential reason why this statement is true, that the displacement is perpendicular to the momentum. Okay, and the fact that it is displaced was initially argued, I believe, by Nick Reed in this old paper, heuristically by looking at the wave function and arguing something about the plane wave factors that you put in. Okay, so this picture was developed in many papers in the late 90s, which I won't really have time to describe. But this was the existing, as far as I can tell, this was the existing physical picture that was being developed in the late 90s to understand the structure of the composite fermion in the lowest Landau level. So what I want to argue is that this picture misses some physics, and further, it's not particle-hole symmetric. It's not particle-hole symmetric because the electric charge changes sign under a particle-hole transformation, but it's easy to argue that the vorticity doesn't change sign. The vorticity is related to the phase of the wave function, and since particle-hole is an anti-unitary transformation, the phase of the wave function remains the same, and so the vorticity stays the same. So the vorticity is not changed, but the charge changes sign. So there's some weird thing that happens to this picture under a particle-hole transformation. So what I want to advocate instead is a new picture for the composite fermion on the lowest Landau level. So the first observation is that any wave function of fermions in the lowest Landau level is described by an antisymmetric polynomial, holomorphic polynomial, times the Gaussian factor, which I'm always going to suppress, of the coordinates of the electrons. Now, any such polynomial can be factorized as a product of Zi minus Zj times the symmetric polynomial of all these Z's. Okay, so that's an exact statement. But this means this first factor tells you that one vortex is sitting exactly on the electron, and that's a consequence of the Pauli exclusion principle. Okay, so Pauli exclusion demands that one vortex necessarily sits exactly on the electron. So in these heuristic wave function based arguments which say that the vortex is displaced from the electron, it's not legal, if you follow that line of reasoning to its logical end, it's not legal to displace the 4 pi vortex away from the electron. You're only allowed to at most displace one of these two vortices, one 2 pi vortex away from the electron. Right? So the picture then is that we'll put one vortex exactly on the electron and displace the other vortex by an amount that depends on the momentum of the composite fermion. Okay? Now, a 2 pi vortex, the 4 pi vortex has at its core a charge depletion of minus E, right? A charge depletion of E. So a 2 pi vortex is a charge depletion of E over 2. So the end, the place where the electron sits, where I've attached this 2 pi vortex, the net electrical charge is E over 2, while the other vortex, which is displaced, that only has the charge depletion, so it has an electrical charge of minus E over 2. Okay? And there's a dipole moment, but the picture is somewhat different from the earlier. There's still a neutral dipolar composite fermion, but the internal structure is a bit different. Okay? So now let's think about what this internal structure implies. If I drag one end of this dipole around the other end, and dragging charge E over 2 around the 2 pi vortex, and so therefore I will have a phase of pi. So these two ends have mutual statistics of pi. Of course, the bound state is still a fermion, because from a long distance point of view, I've not really done anything. I've just changed the internal distribution. Okay? Okay. And the particle-hole symmetry now acts in a very simple manner. It changes the sign of the electric charge, so charge E over 2 and charge minus E over 2 get exchanged, and it doesn't change the sign of the vorticity, but this picture simply goes to this picture, which is equivalent to changing the orientation of this dipole moment by 180 degrees. Right? So that's all that happens. The particle still stays the same kind of particle, but with the dipole moment rotated by 180 degrees. Okay? Now we can try to understand the structure of such a particle by solving a two-particle quantum mechanics problem, right? So one end sees the other end as a source of pi flux, right? So in this two-particle quantum mechanics problem, if we fix the center of mass of the composite fermion and then we solve for the relative motion, we have to solve the problem of a particle moving on a ring with pi flux threaded through the middle. And, that's a simple problem to solve. And we know the ground state is, so the pi flux in the middle leads to a quantization of angular momentum as integer plus a half. So the ground state is a doublet, it's twofold degenerate. And the twofold degeneracy, it's easy to see, is it's actually a Cramer's degeneracy that's protected by this anti-unitary, it's Cramer's under this anti-unitary particle hole symmetry. This anti-unitary symmetry, which rotates this relative coordinate by pi, makes this half integer quantized doublet, ground state doublet, into a Cramer's doublet, and therefore the degeneracy is robust to all perturbations that preserve the C symmetry. Okay? So we see quite naturally that the composite fermion has this Cramer's doublet structure under this particle hole operation in this new physical picture. Okay, but we also know that if we have a non-zero center of mass momentum of a single composite fermion, that this momentum leads to a non-zero dipole moment, and the dipole moment is oriented perpendicular to the momentum. Okay. Now, in this two-particle quantum mechanics problem, when we solve for the structure of the composite fermion in this doublet, the x and y coordinates, the relative separation of the relative vector, the x and y coordinates simply become the x and y components of spin in this doublet space. Right? That's again easy to see. It's just a simple quantum mechanics exercise, which means that this dipole moment has the precise interpretation of becoming the spin, the x and y components of the spin of this two-component composite fermion. Okay? And the fact that this dipole moment is locked to the momentum, that it's always going to point perpendicular to the momentum, is basically the statement that the spin of this composite fermion is locked in the direction perpendicular to the momentum. Okay? Now that's exactly what you expect of a Dirac fermion. At a non-zero momentum, that its spin is tied to the momentum and is polarized in the direction, it's polarized in some specific direction. In this case, it's perpendicular to the momentum. As an immediate consequence, if we form a Fermi sea of these objects, so they fill up to some momentum kf, and we take the composite fermion around the Fermi surface, then the momentum of this composite fermion is rotated by 2 pi. But since the dipole moment is always perpendicular to the momentum, the dipole moment rotates by 2 pi, but the dipole moment is the relative coordinate, and when the relative coordinate rotates by 2 pi, we will get a phase of pi, right? So therefore, there is a very phase of pi that the wave function of the composite fermion picks up as you take it around the Fermi surface. Okay, so that's a physical way to understand where this two-component Dirac fermion came from. Okay, it's a very simple modification of the earlier physical pictures of the composite fermion. Anyway, that's for intuition. But what we really want to do is to have a more calculational derivation of this Dirac composite fermion theory. And it turns out, so Sohn, intuited the answer. It was an amazing guess. That was a correct guess. But, if you just don't want to guess the answer, you want to give some kind of derivation, you had to do something else. And it turns out that the derivation comes from a surprising direction. It comes from understanding the surfaces of three-dimensional topological insulators. Okay? So let me describe the connection between this problem, this classic problem of the Hoffer-Landau level, and the more modern problem of understanding the surface of three-dimensional topological insulators. Why do these things have anything to do with each other? And this connection gives us a derivation and more insight into this particle hole symmetric theory. So to build up to this, to understanding this connection, let's just think about insulators of fermions in 3 dimensions. And initially, we'll think about free fermions, but with a weird action of time reversal, where under time reversal, the electric charge density is odd. Usual electrons, the electric charge density is even, but let's, theoretically, we are free to consider an action of time reversal where the electric charge density is odd. And such things are well known in the topological insulator literature. They are called class A3, for people who know what that means. And this symmetry is distinct from the symmetry of ordinary electrons, where under time reversal, the electric charge is even. But it turns out this is the theoretical problem that's useful to consider. So the surface of, it turns out that with these symmetries, electrons in 3 dimensions can form a topological insulator. And we'll be interested in the surface of such a topological insulator. And just like for ordinary ordinary topological insulators, the simplest such topological insulator has at the surface a single massless Dirac fermion. And this weird time reversal symmetry, which changes the sign of the electric charge, guarantees that the surface Dirac cone is tuned exactly to the neutrality point. Right? Unlike for the usual topological insulators where you can be away from neutrality. Okay? So this is the surface theory. There's a Dirac fermion with some internal spin. It's a 2-component fermion. There's some background, external gauge field that are coupled in as a way to probe the system. So this is not a dynamical field. It's just a probe of the system. Now, with these symmetries, the electric charge is odd under this weird time reversal, which means the electric current is even. Now that means that external electric fields are odd, but external magnetic fields are even. So everything is flipped compared to the standard story. But since external magnetic fields are even, this means that I can perturb the surface Dirac cone with an external magnetic field and retain all the symmetries of my system. Okay? The magnetic field doesn't break any symmetry. So this, but we know famously that a single massless Dirac fermion in a magnetic field develops, not only does it develop Landau levels, famously it develops a Landau level that's exactly at 0 energy. Okay, there's this 0 Landau level, which sits, there's a nu equals 0 Landau level, and there's other higher Landau levels separated by square root b. And this lowest Landau level, by the C symmetry, which changes the sign of the electric charge, that C symmetry guarantees that the 0 Landau level is exactly half filled. Okay? So at the non-attracting level, in the presence of a non-zero magnetic field, I have this complicated this problem where I have a half-filled Landau level, which is, and all the associated degeneracies of the half-filled Landau level. So now if I turn on any interactions, then if I forget about all these occupied Landau levels and the higher unoccupied ones, and focus attention on this highest energy partially filled Landau level, then I'd map exactly to the problem of the standard problem of the half-filled Landau level. Okay, so that's the reason why there's a connection between the theory of the questions associated with the half-filled Landau level and the theory of 3-dimensional topological insulators. Okay, now this is good news for theorists at least. Because this means that we can study, and furthermore, when we obtain the half-filled Landau level this way, by construction, we obtained it in a system where there's exact particle-hole symmetry all the way up to the microscopic energy scales, right? So not only do we obtain the half-filled Landau level, we obtain the half-filled Landau level in the presence of the particle-hole symmetry, okay? So the good news is that this means that we can study the physics of a particle-hole symmetric half-filled Landau level from a new standpoint by thinking of it as something that's realized at the surface of a certain three-dimensional gapped topological insulator. Okay. Now, because there's a gap state, this is relatively easy to study, and we have a number of techniques that enable us to study this state. This is a classic problem. It's a hard problem, particularly when you insist on particle-hole symmetry. So the good news is that we can obtain tremendous amounts of insight into this very hard problem by studying easier gapped system, but the price we pay is that this gapped system exists in 3 dimensions. But that's okay, right? It's still gapped. So the strategy has been to exploit the understanding of the relatively trivial bulk topological insulator to understand the non-trivial correlated surface state, which in turn maps to this old and classic problem in condensed matter physics. So I don't really have time to describe the rest of the story since I have 5 minutes left. But to summarize what we learned, so what we learned using what we know about the topological insulator surface, it turns out that there is an amazing dual description of the surface of the topological insulator. So the standard description is in terms of electrons that form a Dirac cone, right? Plus perhaps whatever interactions the system has. But in terms of strong correlations, it turns out that there's an alternate description of the same surface, which generalizes it generalizes something that's been known for systems of interacting bosons in 2 dimensions for many, many years, going back to work by Bert Halperin in the, I forget, 1978 or something like that. Long before HLR, there was a duality which interchanged boson number and boson vortex, right, in a 2-dimensional bosonic system. Now it turns out that there's similar duality for Dirac fermions in 2 + 1 dimensions. We can either describe the surface in terms of this theory, or we can describe it in terms of a totally different theory, which, has a 2-component Dirac fermion, pretty much like the original electron, though this should be interpreted as composite fermions, as we'll see in a minute. And these dual Dirac fermions, are coupled now to a fluctuating internal dynamical gauge field, and they couple to the external electromagnetic field in basically the same way that as in many of the composite fermion theories, that the flux of this, or in the vortex duality of bosons, that the flux of this internal gauge field is the electric free current, the physical electric free current of the original particles. Okay, so we'll just take for granted that this duality is correct. But once we have this duality, we can perturb both sides of this system by turning on a background magnetic field, which, as I explained, in this theory, gives rise to the Hoffield-Landau level. In this theory, we can ask what it gives rise to. It will be some description of the Hoffield-Landau level. Okay? And what it does is that in the dual description, the external magnetic field maps to the density of these dual fermions. So therefore, if the external magnetic field is non-zero, then these dual Dirac fermions are at a non-zero density. Okay? So then we end up with the theory of the Hoffield-Landau level as a system of these dual Dirac fermions at finite density coupled to a U1 gauge field, but without any Chern-Simons term. Okay? And this is exactly the theory that Sohn, pulled out of his head beautifully. So we end up with an understanding of where the theory comes from through all this detour into 3 dimensions. So the effective action is that there's a Dirac cone for these dual Dirac fermions, not the original Dirac fermions, but these dual Dirac fermions are now at a non-zero chemical potential because their density is non-zero. They are doped away from the neutrality point. And that the anti-unitary particle-hole symmetry, which for the original particles acted as particle-hole symmetry, took side to side dagger, so that the physical charge density was odd under this C symmetry. Now for these dual particles, particle-hole just acts in the usual manner, and furthermore, these dual fermions, these composite fermions, transform in such a way that they form a Kramer's doublet under this symmetry, right? Which is exactly the same structure that this naive physical argument led us to believe. Okay, so I want to make a few comments on this Dirac theory. The first is, so these arguments that I gave, whether the physical one or the one through the field theoretic one, can't really tell you anything about what happens, about non-universal things, what happens at high energies or short wavelengths, right? What they are good for is what happens at low energies, the low energy physics of the system, the universal low energy physics of the system. And for that, we really need to focus just on states near the Fermi surface and not worry about what happens far, far away from the Fermi surface. But what does it mean to have a Dirac fermion if you're not allowed to talk about what happens far away from the Fermi surface? right? So the real meaning of the Dirac is that as this composite fermion goes around the Fermi surface, you pick up a Berry phase of pi. Okay, so that Berry phase, which is characteristic of a Dirac fermion, is it's claimed to be there in this theory. Okay, and the other, actually very crucial comment to make is that though this theory is particle hole symmetric, as we've derived it, say by making this detour to 3D topological insulators, this is not a lowest Landau level theory. So projecting, there's a different condition for what it means to project to the lowest Landau level for Dirac electrons, right? For instance, in graphene, what does it mean to project to the lowest Landau level? So the condition is that E squared divided by the microscopic Dirac velocity should go to 0, right? Now, we are not taking that limit in this entire derivation, right? So in other words, this way of regularizing the half Landau level as the surface of a 3D system enables us to divorce the two issues, particle hole symmetry and lowest Landau level limit, right? So we can tame the issue of particle hole symmetry without taming the issue of the lowest Landau level limit. And that's what's been done so far, right? Am I really out of time? All right, then I'll stop. Sorry?
There's some time for questions, so you can eat into that time.
Yeah, okay. So then let me just say one thing and then I'll maybe stop. Thanks. Okay, so given that this may sound very new, it's all stuff that happened in the last 1 year, I want to point out similarities with an older theory, which also lived in the lowest Landau level, of composite Fermi liquid of bosons at nu equals 1, and compare it with the new theory of electrons at nu equals half. So ideally, the way in which one is supposed to solve a problem in the lowest Landau level is to write the Hamiltonian in terms of density operators projected at the lowest Landau level. And these density operators, after you project it in the lowest Landau level, have some pretty algebraic structure, but it's very hard to tame. Now, in these papers from the late 90s, there was an approximate method proposed to tame this problem directly in the lowest Landau level, where right from the beginning, you're in the lowest Landau level, instead of trying to project to it at the end of the day. And in particular, Nick Reed derived, or rather, from the results in his paper, you can infer an effective action, which has the following structure. There's some Lagrangian of composite fermions that couple to an internal gauge field, and there's no Chern-Simons term for this internal gauge field. But instead, these composite fermions couple to an external gauge field in exactly the same way that vortices usually couple to an external gauge field, right? So this was a theory of a neutral fermionic vortex description of the composite Fermi liquid, and formally this effective action is completely different from H-law, right? The H-law procedure applied to bosons at nu equals 1 would lead you to a different looking theory. Whether at the end of the day they have the same physical properties or not, something that needs to be settled. It's not obvious by looking at the actions that they are the same. Okay? So this is my final comment. So this theory has a very similar formal structure to this particle hole symmetric theory of electrons at nu equals half. In particular, the density of composite fermions in this theory is the flux density and not the electrical charge density, unlike in H-law Jane, but like in this Dirac composite fermion theory. And so how should one understand the relationship between Reed's 1998 theory and the H-law and the bosonic version of H-law from 1983? So it turns out that you can make a connection between these two if you postulate that as you project to the lowest Landau level, the H-law composite fermions acquire a Fermi surface Berry phase that is non-zero. And in this particular case, if you postulate there's a Berry phase of minus 2 pi, you recover exactly Reed's theory. Now the final comment is that Reed's theory, it turns out, has an emergent anti-unitary particle hole symmetry, which then makes it identical to something that I worked on a few years back, but at that time I didn't notice the connection to Reed's story from many years back on a different problem. It makes it identical to the theory of a metallic surface state of a topological insulator of bosons in 3 dimensions. Right? So again, this connection to the TI surface is present both for bosons at nu equals 1 and for fermions at nu equals half. Anyway, let me just stop here. Maybe I'll put up my comments slide, which you can view. Thanks.
I think I'm as confused as at the beginning of the talk.
Sorry. Hopefully you're intrigued, even if you're confused.
So at the end, you especially at the end, you say that the theory. Well, I might have misunderstood what you said, but you said that with this formulation, you are not yet necessarily not in the lower Landau level. That's one question, which I don't understand. I don't know whether I understood correctly. And secondly, can you comment on whether you think, as Bert thinks, that the Harvard theory is the same as the do you have as the same as the
right? So the first thing to say is that it doesn't matter what any of us think. There's a correct answer. It doesn't matter what any of us thinks. There's a correct answer. I don't know what the correct answer is. Is HLR eventually going to be the same as this theory? It might. I'm open to that possibility. I think, as people discuss the issue of physical phenomena, done correctly within HLR more, it will become clear whether or not it's the same. I don't know, Bert, do you agree?
Well, there is a correct answer to the Harvard-Landau level. However, there are two different versions of theory, right? But are you saying that? What's your position?
I don't need to have a position. I know what the answers are within the Dirac theory for some questions, right? And there are some answers within the HLR theory. And as we heard from Bert, if you do them with the adequate level of care, you get answers which I learned from his talk or not. For some quantities, seem to be very similar to what you get out from the Dirac theory. But it remains to be seen whether it will work out to be the same for all quantities. Right?
Well, at some point it becomes a question of semantics, because we start from a theory that's exact. So assuming that so
that is true. Yeah.
All right. So assuming that the Dirac theory is correct, which I believe, then it better damn well give exactly the same answers as the exact HLR theory. Now, of course, we can't solve the H exact.
Right.
So we want to say what is the that's not what you sort of say. Okay, so what is the low energy form of the HLR theory that is the correct form of the? Do we know what the correct form of the HLR theory is at low energies? And we know that, of course, if I go to really short wavelength and stuff, there's going to be an infinite number of parameters like vertex renormalizations that have to be included in both theories.
Yes.
But neither theory is exact for all. You can't. Neither theory is exact without adding an infinite number of parameters like Landau parameters and so forth. So the real question in my mind, I think the question is what parameters are necessary to get a correct description in each of these theories. There are obviously many more parameters. Many of the parameters in your theory are automatically zero. It's a much simpler theory.
Right.
But I think, in my mind, the real question is probably. I mean, it could be that it turns out that for some crazy reason we get agreement of everything so far, but something's going to break down. Yeah. I think the answer is surely if I go to order delta B cubed or delta B fourth, or if I go to short wavelengths or high frequencies, I'm going to have to add a lot of new parameters to either one of the theories to make them give the right answer. And so I think the question is, what phenomena, not are they exactly the same,
right?
What phenomena are this?
What universal phenomena do they differ, if at all?
At a given level of approximation. So the answer of whether they're the same low energy theory or not depends on how you define low energy theory. What is it supposed to calculate? And so I think it's a reasonable order of things that they're supposed to calculate. They give the same answer. And if you go far enough away, they'll start giving different answers. But then I will say, well, that's not a low energy theory anymore. Or you'll say, that's not a low energy theory. We know.
No, so there is, okay,
maybe there's something deeper than that.
Right, so there's a couple of comments that I should make. Right? First of all, the only way to compare the two theories, if you really wanted to compare the exact H-law theory with this Dirac, whatever, since microscopically they have different starting points, the only way to compare is after you project it to the lowest Landau level. Right?
Why should I project the lowest Landau level?
Otherwise, you can't directly compare the microscopic, because microscopics are different. Right? So it's only after projecting to the lowest Landau level that can the two theory be meaningfully compared.
But that's
Right?
taking the limit of the bare mass going to zero,
It-
the actual problem that we're trying to solve.
Exactly. That's right. So then it's not at all clear that exact H-law, right, will, because exact H-law, I don't know how to do it when the bare mass is zero.
Well, that's,
Right?
you don't know what, look, you can't calculate, you have parameters in your theory also. VF.
I know.
Calculate VF.
Absolutely.
It's not in
That.
there, so we put it,
No, as I said, this is also not a lowest Landau level theory, right? So there's two theories, neither of which is a lowest Landau level theory, but for them to really be compared against each other, both of them have to be projected to the lowest Landau level, right? Only then can one really have a confrontation. But the second comment, in terms of, as far as universal properties go, right? So at the level of fixed points, we can ask whether the fixed points are the same or not. And as you said, I personally, I agree with you completely. There's this theoretical device that we can use of adding an interaction that's slower than Coulomb, right? 1/r to the half, right? And when you do that, there is a H-law fixed point where the coupling to the gauge field is sort of renormalized away to zero, and that's a Fermi liquid fixed point, right? And then in the Dirac, that fixed point has no Berry phase, right, on the Fermi surface. And then the Dirac theory with that same interaction also has a fixed point which has a Berry phase. But no Berry curvature. But it does lead to, very direct consequences for things like this 2kF scattering.
well, okay, that you have to show proof.
Right. So
far, nothing I've seen.
I know, but there are comparisons like that can and should be made, right? So till then, we won't know the answer of, yeah.
I mean, there is a third theory which is microscopic theory.
Right.
And within that, one can show that it's particle hole symmetric, and many of these problems are not shared by the microscopic theory, and it also gives you a pi phase.
Right.
How do you know it gives you a pi phase?
We can show.
Whether there's a pi phase or not depends on how you define a composite fermion.
Yes.
Fermion is not a measurable quantity, so you can have two theories that are exactly the same, in which one of them has a pi Berry phase and the other doesn't. They're exact. You can define composite fermions in two different ways. They're not physical quantities. The question is,
Yeah.
do they make the same?
So that's why it's easier to discuss that at the level of the field theory and the fixed points. So if I do have a fixed point in which the gauge coupling is renormalized to zero, then whether there's a Berry phase or not is a fixed point property, right? It's a universal property of the fixed point, right? So it looks as though on the face of it, these two fixed points are different fixed points. Now, it may be that there's some subtle reason why, in fact, secretly, they are dual descriptions of the same fixed point. Now, that is the question, right? And you ask me whether I have an opinion. I don't know, right?
I have another question. So, in the Dirac description, it also has description of all the fractional Hall states.
Yes.
So you have a way of seeing how you can get two components at filling factor 1/2.
Right.
But how about at filling factor 1/3 or some other
Right.
fractional Hall filling
So
factor?
once I have this effective action at nu equals half, I can then describe all the Jane states, get the right quasi-particle statistics and charge and everything. All that follows, just like it did in the old H-law.
Starting
So
from the
the two
wave,
components.
starting from the wave function.
Well, no, we don't have a wave function that particle holds. We don't have an illuminating wave function that is particle hole symmetric and captures this Dirac structure at nu equals half. We have a wave function, we meaning the community has a wave function, which is not illuminating, it's the DMRG wave function, which is particle hole symmetric, but you can calculate with it, but it doesn't give you direct insight.
So you had this picture of taking this vortex and splitting it and so on. So
Yeah.
does it lead to a different variational wave function, or I didn't get
No, any
where-
no any wave function will have that property that there is a ZA minus ZJ factor out front. Right? It's a question of what. Yeah, we are trying to do something that in that when I tried to build a physical picture, we're trying to describe a single composite fermion. Now you can ask, what does it mean to describe a single composite fermion? What we really know is the many-body state, right? But we're trying to build intuition, right?
wave function? You're saying it's
No. Any lowest ladder level wave function has that property that the polynomial can be, just from Pauli exclusion, can be written as ZA minus ZJ times the symmetric polynomial. Right?
Okay, with that, let's end this.